What's up, everybody? Welcome back to the channel. First, I want to say thank you to everybody. We hit 500 subscribers, and that's awesome. I can't really imagine one person wanting to listen to me talk about stuff, let alone 500 of you. So I really appreciate that. Thank you so much. All right, so with that being said and that out of the way, what we're going to go over today, I'm going to do a two-part video series. The first one is going to be generic, what it is, and then the second part will be how pilots use it. So the first one, we're going to talk about the power plant, so the engines on the aircraft. And what we're going to start off with is kind of just a very generic breakdown of the engine. Not anything too in-depth, but not anything too in-depth, but not anything too layman either. Okay, so I'll try and kind of make it a little bit of both. So the second part of it will be how you use it as a pilot. So, if you're a pilot, maybe you want to just watch part 2 when it comes out and then kind of ignore part 1. But if you're interested in a little bit more in-depth about the power plant itself, then you can watch this one as well. So let's go ahead and get started. So let's talk about what the 7.6 has, right? So the 7.6, there's 3 different types of engines that the 7.6 could have, right? The first one is the most typical, the one that you're going to see the most, and that's going to be a GE CF6 80C2 engine. Now, there are some variations to the C2 engine, depending on the 3 numbers that come after that, or the letter and numbers that come after that, depend on how much thrust you have, essentially. Then we have the Pratt Whitney 4000 series. That's another one that is fairly popular on the 7.6. You got the 4050, 4060, so on and so forth. Rolls-Royce, there were some, but very few. So I just put that on there to say that, yes, there may be a 7.6 somewhere that has a Rolls-Royce engine on it, but we're not going to talk about that. We're going to focus more on the GE, on the CF6, and on the Pratt & Whitney. That's what we're going to focus on, because that's what most of the aircraft have on them. So to start off, we got specifics on the CF6. Now, I said it depends on what version of the CF6 you have. It depends on how much thrust the engine gives you. So if we look, there are 4 different types of the CF6. We've got the B2F, the B4F, B6F, and B7F. Okay. They range anywhere from 52.5 to 62,000 pounds of thrust. It all depends on your series. So obviously the B2F is the 52.5, B4F is the 57.9, B6F, which seems to be the most common that I've seen on 7.6s. That's 61,500 pounds of thrust, and then we've got the B7F at about 62,000 pounds of thrust. Now, are you really going to notice a difference of 500 pounds of thrust between the engines? Probably not. But if you're coming from an aircraft that weighs less than the amount of thrust that one of these engines have, you're going to notice a big difference. Everything starts to happen much faster, right? So these engines are built on what's called a twin spool, or a dual spool, or a double spool. You'll hear them. It's all interchangeable. It's all the same. Basically what that means is we have an N1 rotor and an N2 rotor. And I'll show you kind of a little bit more generic picture of what that actually looks like. But essentially you have a low pressure side and a high pressure side. The N1 being the low pressure side. You got a low pressure compressor and a low pressure turbine. And then you've got the N2, which is the high pressure compressor and the high pressure turbine. Okay. That's really the only thing that's different between the N1 and the N2 is whether or not it's high pressure or low pressure. And then these engines are what are called high bypass ratio turbofan engines. Now, what does that really mean? Generically, it means that a lot of air passes through this engine and it bypasses the main portion of the engine. Okay. And again, I'll kind of show you a little bit of what I mean by that. Now, because we have GE and we have Pratt and Whitney, you would think maybe there's a lot of difference between the GEs and the Pratt and Whitneys, but there's really not. So the Pratts, okay, there might be a little bit of difference in thrust, but everything else is going to be relatively the same. When we look at the Pratts, though, we've got a little bit different of logic when it comes to the naming of the engine. So I said it's a 4000 series, right? And when I say it's a 4000 series, because it's all in the 4000s. So you got the 4050, the 4052, the 4056, the 4060, and the 4062. Okay. Now, if you can kind of extrapolate what that means, the number associated in that 4000 series kind of associates with the amount of thrust that it gives you. So the 4050, which is the lowest one, gives you 50,200 pounds of thrust. 4052, you want to guess how much that gives you? 52,000 pounds of thrust. And then the 56,000 or 56 series is a 56,750. And then the 4060 is 60,000 pounds of thrust. I'm throwing a lot of numbers out here. I know. Just go with me. And then the 4062 being the highest powered, you would think would be 62,000 pounds of thrust, but it does round up to 62,000 pounds of thrust because it's the 61,600 pounds. Okay. So in the Pratt series, you have 5 variations of engines that you could have in the 4000 series, whereas in the CF6, you only have 4. So that's the main difference here. The engines are still twin spool, dual spool, whatever. They still have an N1 and an N2, and they still have the high bypass ratio turbofan, designation associated with it. Now, even though I said I wasn't going to talk about it, the one difference that you will see in the Rolls-Royce that I don't have listed anywhere in here is the Rolls-Royce are typically a triple spool or a 3-spool engine. So there's an N1, an N2, and an N3. So the main difference is really what's going to be driving the accessory gearbox and then how the engine gets started. They also make a little bit more noise. They have more of a whine to them than they do in the Pratt and the GE engines. I guess it's because of the triple spool. I don't really know what causes it. I just know it sounds a little bit different. Now, one reason that you don't find the Pratt or the Rolls engines as prevalent as the Pratt or the GE, part of it is that they just didn't order a lot of them, right? So like companies wanted something that they knew, which was GE or Pratt. But the cost. So like if we think about cars, right? So when you think about GE, do you think immediately and go to aircraft engines? No. You go to like light bulbs or you go to like appliances, right? Pratt and Whitney, you go kind of immediately to aircraft engines. At least I do, because I've never heard of them anywhere else other than aircraft engines. Now, when you go into Rolls-Royce, what do you think about when you first hear that? You think of a Rolls-Royce car. Now, at least I do. Now, when you think about a Rolls-Royce car, okay, GE, I immediately go to dishwashers, refrigerators. So I'm thinking anywhere between like $700 to $2,000, $3,000. Rolls, I think of the Rolls car. So now I'm thinking of a lot higher ticket item, right? A lot more expensive. Same thing happens when we talk about aircraft engines. GEs are more prevalent. Being that they're more prevalent, the cost of operating a GE engine is slightly cheaper. Now, nothing in aviation is cheap. I understand that. Nothing in aviation is cheap. You pay $80,000 for a switch, for crying out loud. Or maybe that was just the military. I don't know. But the difference between a GE engine and a Rolls engine, as far as operating costs, because there are so few Rolls and there are so many GE, is enough to turn a lot of people off. I don't have specific numbers for you. I just know that it is more expensive overall to run a Rolls-Royce engine. also, being triple spool kind of runs into the issue of being more expensive, right? Okay, so let's take a look at like a generic. Let's take a generic look of what this really means. So the N1, like I said, we have what's called an N1 rotor. So that consists of the giant fan on the front of the aircraft. So, or the front of the engine. So that giant fan that's on the front of that engine. So this big blue thing right here on the front. Okay, that is our N1 fan. All right. Then it goes through this portion here. This is the low pressure compressor. Low pressure compressor. It's a very difficult thing to say 10 times, but it's a compressor where it compresses the air into the engine. Now, if we want to think about a jet engine, the easiest way to remember how a jet engine works is what? It's the same thing for internal combustion engines too. It's suck, squeeze, bang, blow, right? It's that 4-cycle thing of the air moving through there. And I'm going to say, I am really surprised I got through that without laughing. Okay. Anyway, so suck, squeeze, bang, blow. So intake of air, compression of air, ignition of air, and then exhaust of air. That's our 4 cycles. It's the same for an internal combustion engine. It's the same for a jet engine. All right, or a turbofan in this particular case. So the big fan pulls the air in. That's the suck portion. So it pulls that air in. The compression portion, this next portion right here, okay, compresses it in and shoves it through the engine. As it goes through the engine, it gets back here to the low pressure turbine. And when it gets back there, the air gets rapidly expanded. And when it gets, that's what causes our thrust. Now, the reason it says 80% here is because this is what gives us 80% of the thrust in a high bypass engine. Okay, notice how there's all these internal parts right here, right? So all of those internal parts get bypassed by a lot of this air that is basically coming through this fan. So it comes through here and then out, and through here and then out. Okay, so it's bypassing a lot of the engine. So that N1 is what is actually giving us most of the thrust on these big turbofan engines. Now the N2, on the other hand, that N2 rotor is actually on the inside. Now realize these are two independent spinning items inside this engine. They are independently spinning from each other. Okay? However, one does affect the other. So even though they spin independently, they still have an effect on each other. Okay? Now, the way you know that they're independent, you know what? I'll talk about that in just a sec when I show you the indicating portion of this. So this is where 20% of your thrust comes from, is the N2 rotor, or basically that internal portion, right? So this is 20% of it's the center line or the internal compression of this. Now remember, we have a high pressure compressor, which is this thing here in the center. We got our high pressure compressor. See, I told you it's hard to say a lot. And then our high pressure turbine. So we've got our low pressure and our high pressure turbine that are next to each other, which is that blue and the red there at the end. And then we've got our low pressure compressor up here in the front and our high pressure compressor in the middle. All right, I said a lot of words, so let's think about it again, okay? The blue portion is our N1 rotor. It's our N1 section, okay? It's our low pressure side. The low pressure side is going to provide about 80% of the thrust for the engine. So 80% of the roughly 60,000 pounds of thrust that we get out of these engines. Now realize this is the same whether it's the CF6 or if it's the Pratt Whitney. The only thing that's going to be slightly different inside the engine is the location of certain items. So where the turbine and where the compressor is inside that internal mechanism, it might be a little bit different. So this is kind of a generic look of a GE, but the Pratts aren't going to be much different. It all still is going to work the same. The high bypass air from the big fan, the N1 fan, is still going to provide 80% of your thrust, and the N2, that internal portion, is still going to provide the other 20%. Just realize that it may not look exactly like this on the inside. And honestly, if you're a pilot, you don't care, right? Even if you're a maintenance guy, looking at this picture, it's just we're talking about theory, and we're talking about what actually happens, not where the stuff is located per se in a specific engine. Okay. Now, the little portion here on the bottom, so this section right here, okay, this is what a lot of people would say is a pretty important piece. Okay, and you can see it's connected right here, right? And then it comes down to here and then out to here, right? Can anybody guess what this is? Maybe? Sorta? No? Put it in the comments if you can guess what it is before I say it. It is our accessory gearbox. So, again, this is a very basic picture of this, right? I'm going to show a more in-depth picture in just a second. But the accessory gearbox is what drives a lot of the stuff that you care about when you're in the flight deck. And what do I mean by that? So it's going to help drive the internal fuel pumps inside the engine. It's going to help run the hydraulic, the engine-driven hydraulic pumps. It's going to help run, the generator, the IDG. It's going to help run the IDG. A lot of the stuff that comes off of this engine as far as power or pressure is going to be driven off of that accessory gearbox, and that accessory gearbox is ran off of the N2. If you watch the engine video or the power plant video that I did earlier, when I talk about the 7.6 power plant and I talk about the importance of a specific number, that number is 50%. And that number is 50% N2. Okay? That's what drives a lot of things. That's what drives things going into different modes. It's what shuts off your starter valve or closes your starter valve. It's what puts the start select switch back into the auto position. It's what determines whether or not the engine is running, right? If we're in flight, we have a dual engine failure. That means both engines below 50% N2. Now, that is an important number because that's what's based off of the speed card and all that kind of stuff, right? And we'll talk about that here in just a second. But just to kind of show that accessory gearbox isn't actually inside the internals of the engine. It's actually driven off the side of it, right? So they've got that one, they have this one shaft here that's ran off of the N2. So the N2 spins, it spins that one, and then it drives that gearbox via a bunch of, gears and shafts and whatever else that run in here. You could see how that is a critical part of the engine. Now, if we look here, this is a more detailed look out of a maintenance manual for the 7.6 GE engines. Okay, so this would be more of a CF6. I've got a couple squares on there that kind of show a little bit about what gets ran off of the accessory gearbox. Not everything in here gets ran off the accessory gearbox, and not everything in here are we going to talk about. But you can kind of see when you look at this where certain things are that you might care about as a crew member on the airplane or in the flight deck or trying to troubleshoot stuff. So if you have something where, like, let's say the EEC fails, which we haven't even talked about the EEC that's going to be next, but the EEC computer, look at that, it's located right here on the left side of the engine. We've got ignition exciters. Now, what are the ignition exciters? These are things that excite the ignition, right? So they send power to the ignition to get the ignition to fire. We've got our engine mounts, our scavenge pumps for the oil. We've got the transfer box. So if you try and remember that generic look, right? So that generic look into the detailed look, right? So this is where we have that drive shaft coming off of the N2 to go into this transfer gearbox. And then as it spins, it's going to transfer that energy to the actual accessory gearbox, which is going to have things like our IDG, and then things to help run fuel pumps. See, we've got a fuel pump over here. You're going to have some other things that aren't necessarily listed on this particular picture, like your hydraulic pumps and things like that are going to be ran off of this section. Okay. Now, obviously, when we talk about certain things and we talk about different indications and that kind of stuff, it is important, at least for me, it's important to know where some of these things are located. So, like oil tanks, for example, if I say, where's the oil tank? Well, I would think, just like a car, I would think the oil tank would be somewhere down here in the bottom. But it's not. It's actually located right here on the right side of the engine. So your oil tank is actually located right there, basically on the outside, inside the nacelle portion, right where your plane of rotation would be for your N1 fan. Now, inside here, we have our IDG air oil cooler here. We've got a hydromechanical unit that is farther in depth than I really care to go for this one. But it helps with the fuel delivery. But, I mean, it's crazy to think about, for me, that the oil wouldn't actually be located on the bottom and have it suctioned out of there. It is actually next to the N1 fan, which is nuts to me. Now, I mentioned EEC, and I brought that up prematurely because I do talk about that on the next slide. So these engines are what is known as FADEC. And not all of them are FADEC. I understand that. The majority of them are, at least from what I've seen and in my experience, they're FADEC. FADEC stands for Full Authority Digital Electronic Control. Okay. This means the engine does a lot of stuff on its own, or based off of inputs from other things. Okay. So when we look at this, your EEC is the main driver for this system. So think of the FADEC like we think about like with the FMC, or we think about it with the IRS or something like that, where FADEC is just the name we give it. It's not a specific thing on the engine. It is an all-encompassing word or acronym for all of these different items working with each other. Okay, so when you have things like the ICAS, or you have things like the thrust reverser switches, fuel control switches, when you have all of these different things listed, they are all part of the FADEC system. And inside that FADEC system is what's really going to control what the engine's allowed to do. Whether it can go to full thrust, whether it has to kind of hold off because the engine, you can't go that high, you'll overspeed it, or you'll over boost it, or over, whatever, over thrust, whatever you want to call it. That's where your thrust management computer, your air data computer, the flight management computer, all of that stuff gets worked through your EEC. So when you change things in the FMC, when you say, okay, we need to run 0.7 Mach, or we need to run 320 indicated, or we need to run whatever, that information comes from the CDU into the FMC, and then the FMC runs that information to the EEC. And this is all pretty much instantaneous. Pretty much. And because it's being instantaneously done, the engine adjusts itself as it needs to be able to meet the requirement that you gave it. So it's still garbage in, garbage out, don't get me wrong. But once that information comes into the EEC from these three things, thrust management computer, air data computer, flight management computer, it then sends this information out. It sends this information out to the hydromechanical unit, which is then going to go to fuel control switches. And then there's going to be information going back and forth between the fuel control switches and the EECs. Now it's just a bunch of word salad for the most part, but all of this is happening just because you changed from 0.8 to 0.79. All of this information has to run through all these different computers to get the engine to slightly slow down. And you can see there's even this thing called a PIMU, PIMU. I don't know. That just sounded good to me. But this is what's called your propulsion interface monitor unit. Okay, so propulsion interface monitor unit. So it goes out to that, and it goes out to your ICAS, your engine indicating crew alerting system. Okay, so your propulsion management unit, or monitor, I guess, your monitor unit, is going to monitor how much propulsion you have. ICAS is going to display the information on your screens to tell you, did it do what I said it should do, right? Then I have my standby engine indicators that are there if needed. And then they're going to get the information from the EECs. Your control alternators, your temperature pressure sensors, fan inlet temperature, all of that goes into the EEC for it to be able to make its decision of what it needs to do for things like max thrust. Okay? A lot of people seem to think that if I go full thrust, full throttle, whatever, I take those thrust levers and I punch the screens in the front of me, and the engine's just going to scream out of control and do exactly what I told it to do and give me the most thrust that it can produce. Not true at all. If you have an EEC, or an electronic engine control, the EEC is actually going to stop you from overspeeding that engine, or putting too much thrust to it, or putting too much power, or getting too much power from it where you can cause internal damage. Okay, this is where the EEC is very important. Now, operationally, on the pilot side, does any of this matter? No. You just want the thing to work. That's what you want. And then it causes some things for you to watch. So once that information comes through the EEC, and once that information gets dispersed to where it needs to go, and you get the signals and everything where it's supposed to go, it goes into what is called the indicating system. And the indicating system, like I said, is basically your ICAS, your engine indicating crew alerting system, right? So engine indicating would be the portion here that would matter. So you can see how if there's any kind of faults, it goes through your propulsion monitoring unit, and then it goes through your ICAS computers, and you can see that here. So fall data comes out of the EEC, goes into the PIMU, the monitoring unit, comes out of there, and then once it comes out of there, it goes down into your ICAS computers, and then the ICAS computers will send it out to your screens. Things that you're going to see on these screens are going to be N1, EGT, N2, and engine vibrations, as well as fuel flow. Fuel flow gets put on here too, but that kind of comes from a different. That comes from the fuel flow monitor, and then it comes in that way. But the big things here that we're talking about is the N1, the EGT, and the N2, as well as your engine vibrations. Notice there's also this thing called your speed card, the N2 speed card. So that's the importance of that 50% N2, and it sends that information to that speed card, and then allows it to do what it does, which is kick your starter out of ground and things like that. Now the AVM that's our engine vibration monitoring system. Off the top of my head, I can't remember what the A stands for, but it's the vibration monitor is what that is. So you have core engine vibes and you have fan engine vibes, and then those will actually show up on your vibration, on your engine vibration. It'll tell you whether it's the N1, the N2, or broadband, which is BB, meaning I have no idea where it is, but there's a vibration somewhere. Then we have what is called an EEC alternator. Okay, and this is important to know. The EEC alternator. So I've heard it called two different things. I've heard it called a PMG, which is a permanent magnetic generator, and then I've just heard it called an alternator. Either way, if we think about your car, for example, your car has an alternator. When the engine starts, it starts from the battery in your car. Engine starts, the alternator takes over, keeps that power going, and then charges your battery. That's essentially what happens, right? It's very broke down, but still. On an aircraft engine, it does kind of the same thing. Your engine starts via air, right? So we put air to the engine, it spins your N2. That's what allows us to start that engine. Once the engine is started, that EEC alternator runs your EEC or powers your EEC. So that's the other name. It's a PMA or PMG. So permanent magnetic generator, permanent magnetic alternator, right? It kind of means the same thing. Alternators tend to give you better power. So I guess it really just depends on how you want to look at it. But an alternator also is a generator. It generates power. What this means is, if I lose my electrical system, if I lose my AC or DC electrical system, my EECs should still work. And that's because they are self-powered. So the EECs are self-powered. Long as that engine is running, that EEC should have power. Okay? Now let's talk about, or have a better picture of, the actual indicating system, right? So the actual indicating system is not very complicated. We've got our N1 here at the top. So this is our upper ICAS. This is our lower ICAS. On the upper ICAS, we've got the N1 and the EGT. EGT, exhaust gas temperature. All right, tells you how hot the engine is. Big things to stay away from are going to be the yellow or amber and red line limits. There are some caveats to that. During takeoff or MCT, max continuous thrust, you can get into the amber range, and it's inhibited for 5 minutes. 5 minutes on two engines, 10 minutes on one engine. Red line's never inhibited on the EGT. On the N1, however, the N1, there's a few more indications on here. We've got our little green arrow. We've got our our computed max thrust, and then we've got our red line and our amber bands, our cautionary stuff here. Now, obviously, I took this out of a scenario I was running in X-Plane, so that's why the hydraulic quantity is there. It's just ignore that; it doesn't actually exist. And then the parking brake. Okay, if you're sitting and you're parked, that parking brake's going to be there. So this is, not going too much into what the ICAS is, but this is where your cautions, warnings, and things like that will show up, advisory messages. So this little green caret is actually what your takeoff or what your N1 setting is, whether it's for takeoff, whether it's for climb, whether it's for whatever. That is what your N1 setting is set to. So if I'm going to go in here and manually set my N1, it will say man for manual, and then I'll be moving that little green caret. This is what the computer says is our max thrust. Notice how they're the same on this one, because it's a max power takeoff. So that little amber band on the inside, that amber radial, is what your max thrust computation is. And that comes from your thrust management computer, and that comes from like all the inputs you put for temperature and density, altitude, pressure, altitude, all that kind of stuff gets put in, and then it displays that. Okay. On the lower ICAS is where you get a lot more of your indications of what the engine is doing on its own. So you've got N2 and fuel flow, and then your engine vibes are going to be here. This is all based off of your oil. So N2 being that N2 rotor, and then fuel flow being how much fuel is going into. This is based in thousands of pounds, so that is 2.1 thousand pounds of fuel going into that engine an hour. So you figure 2.1 is 2,100 pounds per hour. Okay. Typically, these are about 10,000 pounds an hour for a normal burn, not one engine combined. So you got about 10,000 pounds per hour combined. Um, and again, that's a rough estimate, right? Now the reason, remember, I said the N1 and the N2 are separate, right? They're individually spinning. How do I know that? Just by looking at this. Well, if my N2 and my N1 were not independent, if they were dependent on each other, my N2 and my N1 should be the same number, right? If I'm running 75 on the N2, I should be running 75 on the N1. If I'm running, whatever on one, the other one should compensate, but they're not. The N2 spins much faster. It allows doesn't really allow. I shouldn't say it that way. The N2 spins independently, and by it spinning independently, it starts pulling that air through, and then that N1 starts going, and then it all kind of works together, right? So the faster one goes, it helps pull the other one in and do some other, without having the pictures, it's very hard for me to say it, or being able to draw anyway. I really need a better setup. But the N2 is the beginning. Without the N2, the N1 doesn't spin. It just doesn't. And that's where your starter comes in. So you have the air coming in from the starter, and it starts to spin that N2 rotor, and it gets to a certain point with max motoring or a certain percentage based on whatever your company says. You add fuel, there's ignition, that N2 really starts to spin hard, right? And it, the N2 rotation comes up, then your N1 rotation comes up, and then you're generating thrust at that particular time. Now, as I said, the vibrations. Notice how the vibrations do not have any type of band on them, meaning there's no amber band, there's no red band, nothing, right? That is because there is no technical limit on engine vibrations. There's just not. Now, that doesn't mean that you should be flying with an engine that makes you spill your coffee when you're trying to sit there and fly. Like if you're sitting there and you're doing this, okay, vibrations are probably out of control. But there is a possibility, and I'm sure maintenance has their own numbers, right? Maintenance has their numbers. I'm not saying that there aren't limits per se written in a manual somewhere for maintenance. But as far as aircrew, or operationally speaking, there are no limits for you to memorize and say, oh yeah, I can't see more than 4.5 N1, or I can't see more than 4.5 N2, or there's no numbers like that. So what does that mean? Not much. This gauge allows you to see where the vibration is coming from and to be able to communicate that with maintenance for troubleshooting. That's really what this gauge is good for. So you look at it and be like, okay, there's a vibration. I feel a vibration. I see that there's a vibration. You write the number down. Obviously, you probably want to have other information in here. You probably want to look at what your N1 setting is, what your N2 is doing, what your EGT is doing. Okay, and my vibrations are 4.5, and it's pretty bad, right? And then you want to see if it says whether or not it's N1, N2, or broadband, because that again will help with troubleshooting. If it's N1, that tells me it's part of that N1 rotor. It's part of my low pressure side. If it's N2, okay, now it's on the high pressure side. If it's broadband, sorry, maintenance, you're going to be doing a little bit more troubleshooting. Because broadband, you just don't know where the vibration's coming from. It's just like, yeah, there's a vibration in the engine. It's pretty significant. I don't know where it's coming from, though. So, yeah, it kind of sucks in that case. Going up from there, we got oil quantity. Oil quantity is going to be company specific. Most companies say 17 quarts of oil is what's required for dispatch. It'll go down once the engine starts, obviously, but it should never go up. The engine should never make oil based off of you starting an engine. Okay, I'll explain that in the next slide. Oil temperature, okay, we've got an amber band and a red band for oil temperature. That tells me that the oil temperature is getting too high. We don't have low oil temperature warnings because that's fine. If the oil wants to be cool, it can be cool. We prefer it to be cool. We just don't want it to get too hot. Getting too hot can be a sign of low oil quantity as well. Same thing with oil pressure. Oil pressure, okay, we don't really care about the high end so much. We care about the low end, right? If we're losing pressure. So we've got an amber band and a red band on it. Again, low oil pressure is also another sign of low oil quantity. Okay. Now, why am I hitting that? If you watch the engine video, you'll know that low oil quantity is a normal thing in these engines. So there is a low quantity awareness band, which is this thing right here on the oil quantity. And the low oil quantity awareness band is 4 quarts. That's where that band is at 4 quarts. But nothing happens. It doesn't turn yellow. It doesn't turn red. It doesn't do anything like that. It's just telling you, hey, your oil quantity is low. That should be an indicator for you to check your temperature and pressure. Because if your oil quantity is low and it's actually low, your temperature will go up, pressure will go down. Simple as that. If you don't have the liquid, it can't be pressurized. Which then turns what little bit of liquid you have in there to overwork. And when it starts to overwork, what happens? When any of us overwork, you get overheated. So your temperature goes up. Okay? So if we think about the acronym that everybody seems to use to remember this, HOTLOP, HOTLOP, high oil temperature, low oil pressure. Okay, so if you have that, there's other things that we need to talk about. We'll talk about that in part 2 when we talk about on the operations side of things. But HOTLOP, high oil pressure, low oil temperature. Okay, that is going to be a huge determining factor on what you do with the engine from that point. Now, why do I bring up the oil quantity? Let's look at the oil system. So we talked about the oil tank. The oil tank's located on the right side of the engine towards the front inside that cowling. All right. There is a possibility that you will run the engine at such a setting that you'll suck all of that oil out of that tank to where it does not indicate a quantity. Okay, you've got that oil quantity transmitter that's going to be located right here. So here's my tank, here's my transmitter. That transmitter, if there's no oil in the tank, it's going to say 0 oil quantity. Your best indication of whether or not you actually have low quantity is going to be temperature and pressure. Okay? So if I show 0 in flight, if I show 0 on that oil quantity, but my temperature and pressure are within normal range, I'm good. If I show 0 and my temperature is going up and my pressure is going down, I now have a problem, and I'm probably going to want to look at my QRH for things like a drive light or things like a precautionary shutdown. Okay. Now, again, go by what your company says, go by your company directives. I am just some guy on the internet who talks about the 7.6 for now. Maybe I'll talk about other stuff at some other point. But for now, I am just a guy that talks about 7.6. Maybe a 7.5. So always do what your company standard is, right? But if we look at this, all right, so the pink is going to be scavenge oil out of the system. So oil comes out of the oil tank. If we want to follow the lines and look at the pretty colors, the oil comes out of the oil tank. It goes through what's called this lube pump. It goes through here. This is where our low oil pressure switch and our temperature pressure transmitter are located. Okay, so that information is taken before it goes into the engine. All right. Now it comes around, it gets out into the bearings and it gets into the engine, and then it gets drawn out of there back through into our lube and scavenge pump assembly. So here's our scavenge pumps that are pulling that oil back out of there and then running it back into the oil tank. If you're running the engine, especially at higher power settings, there is a potential for that oil to get thrown into the system, and it take a little bit of time for those scavenge pumps to pull that oil back in. Okay? If it does that, that's when you're going to have low oil quantity, but your pressure and temperatures will be fine because you're getting the oil in there, and honestly, you're throwing it back into the system as quick as you can. So what it's doing is it's going out of the tank, through all of this, back around, and then through the tank again. But the great thing is it's at the correct temperature and pressure, so you don't have to worry about it, meaning that there is quantity in the system. So once it comes out and it goes through those scavenge pumps, now it comes out again and it goes through an oil temp bulb and it goes through a magnetic chip detector. Okay, so now we're trying to pull, if I'm shearing bearings inside this engine and I'm getting metal coming out of it through the scavenge pumps, now I've got a chip detector that is magnetic that's going to start pulling that metal out. That's still not a good thing. Granted, I don't want the oil, I don't want the metal to be running through my system, but at the same time, I don't want to pull that chip detector and see metal. That's bad for the engine. I don't care if it's a car, I don't care if it's an airplane, it's bad for the engine. All right, so once it does that, now it goes through what we call fuel oil coolers. So what does that mean? I have fuel going in on one side, right? So I have fuel, let me find my mouse here. I got fuel coming in right here, going through. Now, it is not mixing. It's not mixing. It's like a radiator, right? So it goes in and it runs through its pipes, and then I've got oil coming through the other direction, and it's running through its pipes. But the fuel is pulling that heat away from the oil, okay? Because the fuel coming through it is cooler than the oil going through. So it's going to pull that heat away, and it's going to warm up my fuel, which is a good thing. I don't want my fuel to be too cold. I want it to be a little bit warmer before it goes in and gets spread out into the engine. It goes through two of those. Those are my fuel oil heat exchangers. Okay? Goes through two of those, and then it comes back around to my pump, or my filter system, my scavenge oil filter. Okay? Notice it has the letter B on it. That means it is bypassable. It is bypassable, meaning that if it gets full of junk, it can bypass it and go around. Obviously not a good thing to do on a regular basis, but in a particular case where, let's say I am shedding metal from inside that engine, I don't want it going back into my oil tank and then back through the system and throwing the metal back into the engine itself. So it fills up that filter. And then once that filter gets full, now it starts bypassing it. You will get an ICAS message for that saying, filter, oil filter bypass or oil bypass or whatever. You'll get an ICAS message. I can't remember the exact wording of it, but you'll get one saying that it's bypassing the filter and now it's running straight through. So, hey, you want to get that looked at. All right. So after we do that, it goes back through the system, and then it just continues to go around and around and around. Okay. Now, here is one thing that is not brought up ever. It's not talked about ever, but I know that it's happened because I worked for a company where it happened. Your fuel oil cooler, while the two don't mix, fuel and oil don't mix, right? We've already established that the pipes run like this, right? They on top of each other, around each other, next to each other, whatever it is, inside that fuel oil cooler, but they don't intermingle. However, I don't know how it happened. My guess is when it got installed or when something got changed or whatever, it caused a break in that system somehow. And oil and fuel started to mix. Now, I mentioned before that when you start the engine, whatever you started at oil quantity, it should go down. If you started out at 17 quarts and you start the engine, you should not have 17 quarts anymore. It should be lower than that. It should never go up because your engine doesn't make oil. It doesn't give you more oil than you had when you started. If you see that, if your oil starts to go up, I really hope that your company has a thing to look at and say, oh, yeah, I remember this now. If the oil goes up, I need to be worried about fuel being introduced into my oil. Because if there's a break inside that fuel oil heat exchanger, and then the fuel and the oil start to mix, and the fuel starts to run into your oil tank, now all of a sudden it looks like you're making oil, but you're not. All you're doing is adding fuel. Again, this is not something where I am saying that you need to do something. What I am saying is this is from a personal experience at working at a company where this happened on an engine, on a GE engine too. It was a GE engine. They put something into their manual that says, I think it's on the before takeoff check, check your oil quantity. If it's above a certain number, you need to call somebody. You need to call maintenance because your aircraft does not make oil. Okay? That's all I'll say. I'll leave it at that. We're moving on. Last thing we're going to talk about is the thrust reverser system. The thrust reverser system is going to be based on two different things depending on your engine, depending on the type of engine, depending on the model of the engine, depending on whatever. You have a pneumatic actuator, which this one was taken out of a manual that where the GE engines were pneumatically actuated. So a pneumatic actuator is basically taking pneumatics from the engine, directing it to your thrust reverser system, and using it to move your translating sleeve and to lock your thrust reverser into position. The other side of this, you might see it in the 7.5 World too, they're hydraulically driven. So there is a case where the left and right hydraulic systems run your thrust reversers. So there's two different ways for your thrust reverser system to actuate. It's either pneumatically or hydraulically, depending on the engine. So not all of them are going to be the same. So what happens when I pull those levers up? You have what is called a translating sleeve. Okay, the translating sleeve is this back half of your engine right here. Okay, that is your translating sleeve. It does this. It moves backwards. Because what is a thrust reverser? A thrust reverser is taking your thrust and throwing it forward to slow down the aircraft. That's what it does. Ironically, reverse thrust means it's going forward, but it's going reverse of the direction it normally goes. So your translating sleeve moves backwards, and as it moves backwards, yeah, Jesus, okay. See, I leave all this stuff in here so you guys can see that I am a normal person. All right, so that translating sleeve moves back, and as it moves back, it pulls on what is called drag links. The drag links, which you can see here inside here, these drag links right there, the drag links pull on what are called blocker doors. Here they're called blocker door drag links, but I just call them drag links. All right, so the drag links pull on those blocker doors, and then as it pulls, that blocker door comes up. Well, what do you think a blocker door does? It blocks the thrust from going out the back of the engine. It forces it out through what's called cascade vanes around the outside of the engine. So these cascade vanes are going to be these things right here. Right? This little honeycomb looking thing right here. So what ends up happening is it hits those blocker doors and immediately turns and goes out those cascade vanes, and it ends up forcing that airflow out towards the front of the engine. So I don't know. Again, this is me nerding out. That is really freaking cool, right? So automatically the engine separates itself and spins it and throws the thrust back forward. That is just cool. And then when you deactivate the thrust reversers or close the thrust reversers, it slides back forward and puts the engine back together. Now, I know most of you probably already knew that, but I like explaining it. It's cool. Now, there are some other stuff associated with the pneumatic actuator. You got things like you have a flexible drive shaft that helps, do all the movement. You've got the angle gearbox that actually helps with all the movement. But essentially, it's using airflow to shove that backwards and to lock it into place. And then it's just sheer like motion, right? It's kind of like a door hinge. When that moves backwards, it moves that blocker door, and when it pulls that blocker door up, that's what actually causes your thrust reverse. That's kind of cool. When you're doing a walk around and you look inside the back of the engine, you can see those blocker doors and you can see those drag links all the way around the engine to kind of see, okay, everything's in good shape. Because the last thing you want is to pull a thrust reverse, and need thrust reverse for that matter, and not have it and be like, oh, whoops, okay, here comes the end of the runway real quick. Now realize you're still going to have turbine exhaust, right? You still have the 20% of the engine thrust coming out of the back of the engine. The fan exhaust, which was 80% of our thrust, is what's coming out through our thrust reversers. That's where we're talking about high bypass. If it didn't bypass that way, if it wasn't on the outside that way, that air wouldn't come back around. It would, at least not in this way. We'd have to have a different thrust reverse system. Maybe like a CRJ. I think it's CRJ. It's got the two doors that come behind the engine and block it and shove it forward. That would take care of all of the thrust. All of the thrust would be thrown forward if we did that. But, if we think about it, this is a pretty cool thing. I don't know. I like it. Anyway, that's all I got for this one. I know I say that's all I've got. It's damn near an hour of your time. I appreciate you sticking around. I appreciate you watching. I appreciate you sharing, subscribing, everything you can do. Hit the bell to make sure you know when I release a video. If you have any questions, if you have any comments, please leave them down below, or you can reach directly out to me at gsiguybrandon@gmail.com or brandon@gsigguy.com. Did I say Gmail the first time? I hope I did. It's gsiguybrandon@gmail.com or brandon@gsigguy.com. Either way, I get both of those emails. They come directly to me. I respond to them as quickly as I can. Realize this is not my primary job. I wish it was, but it's not. So sometimes it takes me a minute to get back to you. But I will eventually get back to you, I promise. Same thing with the comments. I do try and respond to every comment. So please leave comments below. If you want to see me do a different video, let me know that too, and we can always talk about that. Outside of that, guys, I appreciate you. Thank you for 500 subscribers. Let's keep that number moving up, and I will see you on the next one.